Good morning, class. My name is Akshay, and today we're going to be looking at momentum and collisions. So, our objective for today is to be able to qualitatively predict, in terms of linear momentum and kinetic energy, how the outcome of a collision between two objects will change depending on whether the collision is elastic or inelastic. So, the key factor here is how momentum and kinetic energy will change depending on the kind of collision. So our first problem. Crazy Ellie, 50 kilograms, decides to learn how to bullfight. She stands her ground as El Toro, 150 kilograms, approaches her at an initial velocity of 8 meters per second. She does not manage to sidestep the bull and is carried back with the bull at a velocity of 6 meters per second. The system consists of the bull and the person. Identify the type of collision and its characteristics. So before we get started, let's just identify the basic equation for momentum, linear momentum. So we have P for momentum, and that's equal to mass times velocity. So in this case, we see that Ellie is stationary in the beginning. So her initial velocity is 0, and the bull, 150 kilograms, El Toro's initial velocity is 8 meters per second, and they weigh 150 kilograms and 50 kilograms respectively. The final velocity is when the masses are together, so when the human and the bull are combined as one total mass. The final velocity of the combined mass is 6 meters per second. So now that we've identified our givens, let's see how to move on from this problem. So to identify the kind of collision, we can see if kinetic energy is conserved or not. And we can also prove whether or not momentum is conserved. So by the problem itself, it says that the system consists of the bull and the person. So it's an isolated system, which means that the momentum should be conserved according to the law of conservation of momentum. But just to prove it, we can use the equation. P is equal to mv, and the initial momentum is equal to the final momentum. So when we substitute the values for our masses and velocities, we see that Ellie's mass times Ellie's initial velocity plus the bull's mass times the bull's initial velocity will give us our initial momentum, our total initial momentum. Now our final momentum is slightly different because we have the summation of both masses. We could separate the two as Ellie times the final velocity and the bull times the final velocity, but it's easier to look at it like this. And it's easier to see that this certain type of collision exists. So we have Ellie plus the bull times the final velocity. We see that momentum is conserved when we plug in the numbers, we result with 1200 Newton seconds on both sides, which means that momentum is conserved. Now for kinetic energy, the base equation is 1/2 mv squared. And for initial kinetic energy, we have to find each component of kinetic energy. So since Ellie is stationary, she has 0 kinetic energy. Anything in motion will have kinetic energy. Since she is stationary, she does not have any kinetic energy. The bull, on the other hand, has 4,800 joules of kinetic energy. So when we add both of them up, we result with 4,800 joules of energy. Now for the final kinetic energy, we have to add both masses up for the total kinetic energy times the final velocity, and we result with 3,600 joules of energy. Notice how there is a difference in the initial kinetic energy and the final kinetic energy by 1,200 joules. There is a loss of kinetic energy, which means that it is not conserved, and thus this is an inelastic collision. Now to our next problem. 2 billiard balls, each 0.2 kilograms, are moving to the right. However, the left billiard ball is moving at 3 meters per second, while the right billiard ball is moving at 1 meter per second, according to the picture. After they collide, the 8 billiard ball slows down to a constant 1 meter per second, and the 2 ball speeds up to a 3 meter per second constant. The system includes both billiard balls. Describe the collision and what occurs in terms of momentum and kinetic energy. Once again, we see that the system includes both the billiard balls. Thus, we can conclude that this is an isolated system, so momentum should be conserved according to the law. We can also test whether or not kinetic energy is conserved using the equation 1/2 mv squared. So initially, the masses velocity for the 8 ball is 3 meters and 1 meter per second for the 2 ball. And as we see, let's go back to the problem. We saw that the velocities were swapped for some reason after the collision. This shows that the momentum from the 8 ball was completely transferred to the momentum of the 2 ball, and the momentum of the 2 ball was transferred to the 8 ball. So, and they kept moving on. So that shows that this is not an inelastic collision because the balls do not stick together and they transfer each other's momentum to each other. So back to the solution again, we see that both sides have 0.8 Newton seconds, which means that momentum is conserved. And I'd like to reiterate that both the balls do not stick together in this problem. They are separate, and thus they have their own separate velocities. And we calculated that the momentum is the same initially and finally. So now moving on to kinetic energy, we see that initially there's 1 joule of kinetic energy. And that is calculated by plugging into 1/2 mv squared for both the billiard balls. Now afterwards, we result with the same 1 joule of energy. This shows that kinetic energy is conserved, as it's 1 joule before and after the collision. And momentum is also conserved, and this is what we define as an elastic collision. So what did we learn today? An object which is moving has momentum. The amount of momentum possessed by a moving object is the product of mass and velocity, which we used, P equals m times v. We also applied the law of conservation of momentum thoroughly in this lesson. It is when it occurs in an isolated system where the total momentum initially is equal to the total momentum after a collision. Today we studied 2 kinds of collisions: an elastic collision, where both the momentum and kinetic energy are conserved, and an inelastic collision, where momentum is conserved but not kinetic energy. And like I said previously, kinetic energy is the energy of motion. And in the first problem, where Ellie was stationary, she had no kinetic energy because she was not moving. Thank you for learning with me today. I hope you enjoyed my lesson.